The cosmos holds secrets that rewrite the laws of physics. Hidden in the vast darkness are theoretical giants known as dark stars, objects so strange they are powered by invisible matter rather than nuclear fire. By the end of this journey, you will explore 25 of the most compelling candidates for these undiscovered cosmic monsters, from primordial behemoths to rogue wanderers between galaxies. What if the first stars to ever shine were not stars at all, but something infinitely more ancient and alien? How could a single dark star hold the key to life on worlds without a sun? What do you believe is waiting for us in the dark? These primordial supergiants would have been the first structures to ignite in a universe of pure darkness. Born from vast clouds of hydrogen and the invisible scaffolding of dark matter, they did not shine like the stars we know today. Their power source was something far more exotic, the self-destruction of dark matter particles colliding and annihilating deep within their cores. This process would have generated immense heat and light, fueling a star without ever needing nuclear fusion. The sheer scale of these entities is almost incomprehensible. A single one could have contained the mass of millions of our suns, making our entire solar system seem like a speck of dust in comparison. A star that burns on annihilation would not be bound by the same limits as a fusion-powered star. It could grow to staggering sizes, glowing with a soft, strange light for millions of years. Their existence would rewrite the story of cosmic dawn. Instead of small, hot, and short-lived first-generation stars, the infant universe might have been illuminated by these gentle, colossal giants. They would have acted as cosmic lighthouses, their radiation beginning to strip electrons from the neutral hydrogen that filled the void, a process crucial for clearing the cosmic fog. Their eventual deaths, too, would have been cataclysmic events unlike any supernova we can conceive. A collapse of that magnitude could have directly forged the seeds of the supermassive black holes we now find lurking at the center of nearly every galaxy, including our own Milky Way. So the very structure of our cosmic home, the galaxies we see today, might owe their existence to the brief, brilliant lives of these dark matter monsters. Finding these first giants is a monumental challenge as their light has traveled for over 13 billion years. Astronomers are not searching for a pinpoint of light in a telescope. They are hunting for ghosts, for the faintest echoes of their existence imprinted on the fabric of the cosmos. One powerful method involves the universe's own magnifying glass, a phenomenon called gravitational lensing. The immense gravity of a massive object like a galaxy cluster bends the space around it. This bending acts like a lens, distorting and amplifying the light from objects far behind it. If a remnant of a primordial dark star, or the black hole it became, lies along our line of sight, it could warp the image of a more distant galaxy in a specific, detectable way. Surveys that map the sky are meticulously analyzing these tiny distortions, looking for the signature of invisible, ultra-massive objects that should not exist if our current models are complete. Another clue lies in the oldest light we can see, the cosmic microwave background. This is the faint afterglow of the Big Bang, a snapshot of the infant universe. The formation and radiation of the first luminous objects, including potential dark stars, would have subtly heated the surrounding gas. This heating left a specific fingerprint on the background radiation, a faint signal that new space telescopes are now sensitive enough to potentially detect. The greatest obstacle, however, is time itself. These behemoths lived and died in the universe's infancy. Most would have collapsed under their own immense weight, directly forming the supermassive black holes we now find at the centers of galaxies. They may have left almost no visible trace, having transformed entirely from one cosmic mystery into another. So the hunt continues not for the stars themselves, but for the shadows they cast across eternity. Deep within the swirling heart of a distant galaxy, a second kind of monster might be hiding in plain sight. While we know supermassive black holes anchor most galactic centers, some observations suggest a hidden partner is also at work. This candidate, an obscured Leviathan, is theorized to be lurking in the very core, its presence masked by thick clouds of cosmic dust and the overwhelming glare of the central black hole itself. We cannot see it with any telescope, but its immense gravity leaves a distinct signature on everything nearby. Imagine watching a complex dance where one of the main dancers is completely invisible. Astronomers observe the orbits of stars and gas clouds whipping around a galactic center. Their speeds and paths are mapped with extreme precision. In some galaxies, these motions are simply too fast, too erratic, to be explained by the gravity of the known black hole alone. It is as if an additional, tremendous mass is there, pulling on them from the shadows. The data reveals a gravitational anomaly, a persistent tug that should not exist. For instance, in one well-studied galaxy, scientists tracked a cluster of young, bright stars on orbits that make no sense. They are moving as if they are feeling the pull of two monstrous objects, not one. The measured velocities of hydrogen gas clouds in another galactic core also defy models, requiring the presence of a second, colossal gravitational source to explain their frantic whirl. This is not just a missing piece of the puzzle, it is the suggestion of an entire hidden structure. The obscured Leviathan would be a dark star of a different breed, perhaps a relic from the earliest universe that was captured by the galaxy's core black hole, or a later formation born from conditions we do not yet understand. It is a ghost in the machine of gravity, its existence written only in the impossible paths of the stars it commands. But the most elusive dark stars may not be anchored to any galaxy at all. They are cosmic runaways cast out into the profound emptiness between galaxies. These rogue dark stars would be solitary giants adrift in an ocean of nothing, their journey beginning with a violent celestial event. Imagine two galaxies colliding in a slow-motion dance of destruction, their gravitational fields intertwining in chaos. In such a maelstrom, a dark star orbiting near the periphery could be slingshotted outward at tremendous speed, flung forever into the intergalactic void. It would be a one-way trip into absolute isolation, a star leaving its home behind for good. This exile, however, creates a unique opportunity for discovery. Freed from the blinding glare of billions of sibling stars and the thick dust of its home galaxy, a rogue dark star would exist against a backdrop of perfect inky blackness. Any faint, intrinsic glow it might possess, that soft light powered by dark matter annihilation, would no longer be washed out. It would be the only source of light for millions of light years in every direction. Detecting this faint signal would still be a monumental task, like trying to spot a single candle flame from 1,000 miles away. Yet, in the absolute quiet of intergalactic space, that solitary flicker would stand out in a way it never could within a crowded galaxy. Astronomers could study its pure properties, its composition, and the nature of its dark matter heart without any interference. It would be a pristine laboratory, a wandering relic from the early universe holding secrets about the fundamental forces that shape our reality, all while drifting silently through the coldest, darkest corners of existence. The silence of intergalactic space is broken by a violent, invisible dance. Far from any galaxy, two dark stars could be locked in a mutual orbit, a binary system unlike any other. This pairing would be a gravitational powerhouse, a cosmic engine fueled by their immense mass and the annihilation of dark matter within their cores. Their orbital dance would not be a gentle waltz, but a slow, stately revolution over vast distances, each star a titan in its own right. The complex dynamics of such a system would be a nightmare for our current models of stellar evolution. Normal binary stars are governed by fusion physics and mass transfer, but these dark stars would operate on entirely different rules, their lives dictated by the density and behavior of the dark matter that powers them. How would their dark matter halos interact as they swing around each other? Would they steal this invisible fuel from one another or create a shared annihilation zone in the space between them? The very existence of such a pair would force us to rewrite the book on how dark matter behaves in the most extreme environments. The most profound evidence of their existence, however, would not be in light but in the ripples they send through space-time itself. Their orbital motion would generate persistent, low-frequency gravitational waves. These are not the sharp chirps from colliding black holes, but a constant humming signal, a single note held for millions of years. Future observatories like the planned Laser Interferometer Space Antenna, or LISA, are designed specifically to listen for this cosmic hum. This space-based gravitational wave observatory would act as a colossal ear, tuned to the lowest frequencies in the universe. Detecting the specific gravitational wave signature of a binary dark star would be the ultimate confirmation. It would be like hearing the ghostly harmony of two invisible giants spinning in the dark for eons, finally announcing their presence to the universe. A dark star could do more than drift alone. It could build a family. This candidate is a cosmic cradle, a dark star theorized to host its own system of planets. The very idea shatters our understanding of what makes a world livable. We assume life needs a sun, a stable, fusion-powered star providing light and warmth. But here, the energy source is fundamentally different. The gentle, pervasive heat generated by dark matter annihilation deep within the star's core would radiate outward, creating a shell of warmth in the surrounding space. At a certain distance, this heat would be just right to maintain liquid water on a planet's surface, defining a habitable zone entirely alien to our own. Imagine a world perpetually bathed in this soft internal glow. There is no sunrise, no sunset, no direction to the light. The sky would be a perpetual, deep twilight with the dark star itself a faint, diffuse presence, perhaps a hazy patch of light that never moves in the heavens. The energy for life on this world would not come from above, but from below, from the planetary crust itself, warmed by the constant, low-level radiation. This would create a bizarre and wonderful environment for chemistry to unfold. The planet's surface might be covered in vast, warm oceans, heated from the core outward, with no need for stellar photons to drive weather systems. Volcanoes and hydrothermal vents, supercharged by this internal heat, could become the true engines of the planet's energy cycle, creating oases of chemical richness in the eternal gloom. What kind of life could emerge in such a place? Evolution would follow a path we can barely conceive. Life forms might not need eyes, relying instead on other senses like sonar or sensitivity to thermal gradients to navigate their world. Their entire ecosystem, the base of their food chain, could be built not on photosynthesis but on chemosynthesis, drawing energy directly from the planet's warm, mineral-rich crust and waters. A biological system built on the ghostly power of annihilating dark matter would be the ultimate testament to life's tenacity, proving that it can flourish in the most unexpected corners of the cosmos, even in the faint, warm shadow of an invisible sun. The line between star and black hole might have once been blurrier than we ever thought. We now encounter a candidate so immense it challenges the very definition of a star, a quasi-star progenitor. This is the theory of a primordial hybrid, a star that could have contained a newborn black hole within its own heart. Picture a star so colossal, hundreds of times more massive than any star today, that its own core collapses under the immense weight of its outer layers. In a normal supernova, this collapse is violent and explosive, blasting the star apart. But in the unique, dense environment of the early universe, something different could have occurred. The outer layers of the star, still rich with fresh hydrogen fuel, could have been so incredibly massive and dense that they contain the collapse. They would have formed a vast, luminous envelope, a stellar cocoon, around the newly formed black hole at the center. This is the quasi-star, a theoretical titan powered not by fusion alone, but by the voracious appetite of the black hole it nurtured. Now, introduce the dark matter factor. Imagine if this primordial cloud, the one that collapsed to form the quasi-star, was also exceptionally rich in dark matter. The dark matter particles trapped by the star's immense gravity would have sunk to the core, annihilating and providing a powerful secondary energy source. This dark star quasi-star hybrid would have been an unstoppable cosmic engine. The energy from dark matter annihilation would have helped support the star's enormous structure against a rapid gravitational collapse, allowing it to grow to truly staggering proportions. It could have sustained itself for a relatively brief but crucial period, all while the central black hole fed on the inner layers of the star, growing at an incredible rate. This single object could solve one of the greatest puzzles in modern astronomy, the rapid formation of supermassive black holes. We see these monsters with billions of times the Sun's mass in the very early universe. How did they get so big, so fast, with so little time to grow from smaller seeds? A standard stellar mass black hole would take far longer to accrete that much material. But a dark matter-powered quasi-star provides a perfect solution. It is a ready-made supermassive black hole nursery. The black hole at its center is born into a perfect feeding environment, surrounded by a dense, massive envelope of fuel. The additional energy from dark matter annihilation keeps that fuel from being blown away too quickly, allowing the black hole to feast and balloon in size at a breakneck pace. In a cosmic blink, this hybrid monster could have directly collapsed into a black hole with thousands, even millions of solar masses, a ready-made supermassive seed for the giants we see today. This candidate represents a missing link, a brief, brilliant phase where the laws of stellar physics and dark matter interplay created the ultimate cosmic shortcut. A star that feeds could rewrite our cosmic catalogs. This eighth candidate is a dark matter fountain, a celestial entity gorging itself on an invisible river of fuel. Imagine a star passing through a dense, localized stream of dark matter, a cosmic current flowing through the galaxy. As it moves, it pulls this invisible material into its core, dramatically ramping up the rate of annihilation. This is not a steady burn, but a frantic feast. The result would be a star with a wild and unpredictable heartbeat, flaring with intense bursts of energy in specific high-energy wavelengths. Its brightness would surge and fade in a pattern that makes no sense for a normal variable star. It would not follow the regular pulsations of a Cepheid or the explosive timetable of a nova. Instead, its light curve would be chaotic, a jagged line on a graph pointing to an engine we have never seen. The most fascinating possibility is that our telescopes have already recorded this anomaly. Automated sky surveys have catalogued millions of variable stars, objects whose light changes over time. A dark matter fountain with its strange emission signature could easily be hiding in that vast database, mistakenly labeled as a peculiar kind of pulsar or an unexplained stellar flare. Its true nature would be masked by its own bizarre behavior. This makes the hunt for such an object a digital archaeology project. Astronomers are now going back, armed with new algorithms and a better understanding of what to look for. They are sifting through petabytes of old observations, searching for that one star whose flickering light does not match any known template. Finding it would be like discovering a hidden diary entry in a book we thought we had read 1,000 times. It would confirm that some of the most exotic objects in the universe are not in some distant, unreachable corner, but are simply waiting to be recognized in data we have already collected. Our own cosmic backyard, the vast halo of the Milky Way, could be hiding its own ancient giants. These are not distant theoretical constructs, but potential neighbors, a trio of galactic halo ghosts. Their relative proximity to us makes them some of the most compelling and huntable candidates for dark stars. Imagine searching for something in your own house rather than in a city on the other side of the planet. Because they would reside within the invisible dark matter halo that envelops our entire galaxy, we have a real chance of finding them. But how do you spot an object that gives off almost no light and is lost in a sea of darkness? Astronomers have turned to clever, indirect methods, reading the subtle clues these ghosts leave on their environment. One powerful technique involves watching the movements of other stars we can see. The Milky Way's halo is sprinkled with ancient, lonely stars, each on its own long, slow orbit around the galactic center. If a massive dark star passes near one of these visible stars, its immense gravity would give the visible star a tiny but measurable gravitational nudge. It would be like watching a single floating leaf in a still pond suddenly twitch, suggesting something large and unseen just passed beneath the surface. By meticulously tracking the paths of millions of these halo stars with observatories like the Gaia spacecraft, scientists are looking for just these kinds of unexplained wobbles, a signature of an invisible titan's gentle pull. Another method listens for a whisper of radiation. While a dark star's primary power is annihilation deep within, some theoretical models suggest this process could produce a faint, exotic glow. This would not be the brilliant white light of our sun, but a very specific signature in gamma rays or other high-energy wavelengths. Our space telescopes are constantly scanning the sky, mapping these energetic emissions. Finding a persistent, point-like source of this exotic radiation in the galactic halo, with no visible star to explain it, would be a monumental discovery. It would be like hearing a faint, steady hum from an empty room, confirming a hidden machine is running inside. The hunt for these halo ghosts is a painstaking process of elimination, a cosmic detective story written in the silent language of gravity and light. Finding just one would transform our understanding of the Milky Way's hidden architecture, revealing that our galaxy is not just home to stars and planets, but to something far older and more mysterious. Sometimes the most profound discoveries begin with a single, stubborn data point. The Hubble Space Telescope, observing a distant quasar, noticed something peculiar about its journey. The light from this brilliant object was being bent and magnified by the gravity of a foreground galaxy cluster, a well-understood cosmic lens, yet the image it produced was subtly wrong. The way the quasar's light was distorted did not perfectly align with the amount of visible matter in the lensing cluster. It was as if an invisible hand holding an additional, tremendous mass was helping to warp the fabric of space. This gravitational lens anomaly points directly to our 12th candidate, a dark star acting as a hidden anchor within the cluster. The mathematics of general relativity are precise. The degree to which light bends tells you exactly how much mass is causing the curvature. When the calculation shows a significant mass surplus, an invisible component must be present. In this case, the mismatch was too large to be explained by diffuse dark matter alone. The data suggested a concentrated, point-like source of gravity, an object with the mass of perhaps thousands of suns, yet completely undetectable in any wavelength of light. This was not a smooth distribution of dark matter, but a singular, massive entity. Think of it like looking at a magnifying glass and realizing it is far heavier than it should be, suggesting a dense, invisible weight is fused to its center. This dark star candidate, hiding within a crowd of normal galaxies, would be a gravitational ghost, its presence felt only by the way it twists the light from objects billions of light years behind it. Its existence would force us to reconsider the architecture of galaxy clusters themselves. Perhaps they are not just collections of galaxies held together by dark matter, but also contain these ancient dark leviathans as foundational pillars, their immense gravity helping to bind the entire cosmic structure together. The hunt is now on to find more of these anomalous lenses, each one a potential signpost pointing to a monster we cannot see, but whose shadow is cast across the universe. A star's death usually signals the end of its light, but a dark star could transform into something even more hauntingly beautiful. In its final stages, such a leviathan might begin to shed its immense outer layers of hydrogen and helium, casting them off into the void. This expanding shell of gas would not be lit by the ultraviolet radiation of a hot, exposed stellar core as in a typical planetary nebula. Instead, the faint, persistent glow illuminating this cosmic shroud would come from deep within, from the ongoing annihilation of dark matter particles at the object's heart. The result would be a dark nebula, a luminous ghost in space powered by an invisible engine. To our telescopes, this object would appear as a vast, faintly glowing cloud, perhaps tinged with unusual colors from the specific energies released by the annihilation process. It would lack a sharp, bright central point, its light seeming to emanate from the entire cloud at once, a soft, internal radiance with no clear source. The structure would be ethereal and difficult to define, its edges blending seamlessly into the darkness of interstellar space. Its beauty would be eerie and alien, a celestial object that defies the standard life cycle of stars. It would be a monument to a different kind of physics, a final, glowing testament to the power of the invisible universe, a reminder that even in death, a dark star continues to burn with a strange and silent fire. Some galaxies spin with a secret locked in their heart, a core of stars that whirls defiantly against the flow. This counter-rotating core is a profound dynamical puzzle, a celestial rebellion that should tear a galaxy apart. How can a dense, central cluster of stars orbit in the exact opposite direction to the billions of other stars in the galactic disk? The forces involved are immense, and such a configuration should be unstable, like trying to spin a bicycle wheel backwards while the rest of the bike moves forward. The friction and gravitational interactions should have long ago erased this strange motion, smoothing it into a single, unified rotation, yet we observe it. This suggests a recent and violent event, a merger or an accretion that delivered a package of stars with a completely different angular momentum. But what could provide the gravitational anchor to stabilize such a chaotic situation? The answer might be a dark star, a massive object with a formation history entirely separate from the galactic material around it. Imagine a primordial dark star, one of the first entities to form in the universe, drifting in the cosmic darkness for eons. It is eventually captured by the growing gravity of a young galaxy, settling into its very center. Later, a small, gas-rich galaxy merges with this larger one. The incoming material, with its own distinct spin direction, is drawn toward the core. There, it encounters the immense, localized gravity of the ancient dark star. This invisible titan acts as a dynamical pivot, a fixed point in the chaos that allows the counter-rotating stars to find a stable orbit around it. Its gravity creates a protected zone, a pocket of opposite spin that can persist for billions of years. Computer simulations strongly support this idea. When astrophysicists model galaxy mergers, they often find that counter-rotating cores quickly dissolve without a central mass concentration, far exceeding a typical supermassive black hole. But when they place a single, ultra-massive object with the proposed mass of a dark star into the simulation center, something remarkable happens. The rebellious core of stars settles into a long-lived, stable configuration. The model galaxy spins peacefully, its inner heart beating to a different rhythm, all held in check by the silent, unseen anchor at its center. This candidate does not just explain a strange observation, it provides a living fossil, a relic from the universe's first moments that still dictates the motion of stars today. A star moving fast enough to escape its galaxy entirely presents a different kind of mystery. This candidate is a high-velocity runaway, a dark star catapulted through the void at a staggering fraction of the speed of light. Such an extreme velocity could only come from the most violent engines in the cosmos. One scenario involves a gravitational slingshot around a supermassive black hole. Imagine a dark star in a binary pair, its orbit carrying it perilously close to the galactic center. If its companion star is torn apart and consumed by the black hole, the surviving dark star could be flung outward like a stone from a sling, gaining a tremendous kick from the gravitational interaction. Alternatively, if it were once the dark partner in a binary system with a normal star, and that normal star went supernova, the asymmetric explosion could have sent it careening off on its own at an incredible speed. This journey would fundamentally alter the star itself. As it streaks through the galaxy, it would be moving too quickly to hold onto the diffuse cloud of dark matter that normally surrounds and fuels it. This is its dark matter atmosphere, the halo of particles that sustains its internal annihilation engine. At such high velocities, this halo would be stripped away, left behind like a cosmic wake. The star would be effectively running out of fuel as it travels. This creates a unique and detectable signature. The rate of dark matter annihilation within its core would begin to drop. For a brief, observable period, the star would appear to be a faint, cooling object with an unusual chemical composition, one that is not hot enough for fusion but is still emitting a soft, decaying glow. Its trajectory would also be a dead giveaway, a straight line shot directly away from the galactic center or the site of an ancient stellar cataclysm. Finding such an object would be like finding a bullet frozen in mid-flight, its path telling the story of the immense violence that created it. The runaway star is a fugitive, but the next candidate is a ghost made of pure theory. Dark star number 16 is an action star manifestation, a celestial object born from one of the most promising solutions to the dark matter puzzle. The action is a hypothetical particle, conceived not for dark matter, but to solve a deep mystery in particle physics concerning the strong nuclear force. Yet it perfectly fits the bill for a dark matter candidate, a particle that is incredibly light and barely interacts with normal matter. Now envision countless trillions of these actions drawn together by their own collective gravity. Under the right conditions of extreme cold and density, they would undergo a profound transformation, merging into a single, coherent quantum state known as a Bose-Einstein condensate. This is not a star of burning gas, but a single, gigantic quantum object, a star-sized superparticle. It would be a perfectly smooth, frictionless sphere of exotic matter, a ghostly orb drifting silently through space. Its interaction with the universe would be almost non-existent, yet not quite zero. The action has a unique and telltale property, a fragile connection to the electromagnetic force. In the presence of a strong magnetic field, such as those surrounding neutron stars or within galactic jets, an action can spontaneously convert into a photon, a particle of light. An action star, a dense ball of these particles, would therefore be a ticking time bomb of potential illumination. If such a star were to drift through a powerful magnetic field, the conversion could cascade. It would not be a slow glow, but a sudden, brilliant flash of radio waves, a burst of energy appearing from absolute nothingness. Telescopes searching for fast radio bursts, those mysterious, intense millisecond flashes from across the cosmos, might have already recorded the death cries of these phantom stars. The signal would be sharp, pure, and without an afterglow, a perfect fingerprint of a ghost that briefly flickered into visible reality before vanishing forever. Finding that specific signature in the radiostatic of the universe would be the ultimate confirmation, proving that some of the most elusive dark stars are not massive giants, but fragile, quantum wisps waiting for the right moment to shine. Deep in the void, a star is torn apart by the immense gravity of a black hole. This violent spectacle, a tidal disruption event, creates a brilliant flare of light as the star's material is shredded and heated. But some of these cosmic cataclysms do not behave as they should. Their light curves are all wrong, lingering far too long or glowing with an unusual color of energy that fusion alone cannot explain. This suggests the victim was no ordinary star. The 17th candidate is a dark star imposter, an object whose disruption unleashes a hidden power. When a normal star is torn apart, its energy comes from the rapid accretion of its own gas onto the black hole. But if a dark star, powered internally by dark matter annihilation, were to be caught in the same gravitational trap, the event would be profoundly different. The disruption would not just release gravitational energy, it would violently destabilize the star's core. The delicate balance holding the dark matter fuel in check would be shattered, triggering a runaway chain reaction of annihilation. The resulting flare would be a hybrid monster, part tidal energy, part dark matter detonation. It would be far more energetic and last significantly longer than a standard event, as the dark matter core continues to pour out energy even as the stellar envelope is consumed. The 18th candidate takes this concept a step further, proposing a near miss. Imagine a dark star on a trajectory that brings it perilously close to a black hole, but not quite close enough for total destruction. The black hole's gravity would still exert a tremendous tidal force, squeezing and stretching the dark star like a cosmic stress ball. This violent compression could dramatically increase the density of dark matter particles in its core, supercharging the annihilation rate. The dark star would not be destroyed but awakened. It would flare with a sudden, intense brilliance, a temporary beacon powered by its own internal chaos. To a distant telescope, this would look like a strange, slow-rising tidal event with no clear aftermath, a flash in the pan that fades away as the star settles back into its normal state. These imposter events force astronomers to re-examine their catalogues of cosmic explosions. That strange flare from 5 years ago that never quite fit the model, the one that seemed to burn with the wrong kind of fire, might not have been a star's death cry at all. It could have been the signature of a dark star's heart being violently exposed, a brief, brilliant glimpse into a hidden universe of power. High above the swirling galactic disk, vast rivers of gas arc into the halo, a phenomenon known as a galactic fountain. We have always credited supernova for this cosmic hydraulics, their violent explosions blasting material out of the disk. But what if a quieter, more persistent power source is also at work? Concealed within one of these rising streams could be a dark star, its gentle but constant output of heat helping to drive the entire cycle. While a supernova is a sudden, immense shockwave, the energy from a dark star would be a steady, pervasive warmth. Imagine a heating element placed at the bottom of a pool of water, causing the liquid above it to slowly rise. This dark star would act in a similar way, its low-energy radiation subtly heating the surrounding hydrogen gas, giving it the thermal push to buoyantly lift away from the disk and join the fountain's flow. Finding it would require a new way of mapping the sky. Astronomers would need to look not for a single point of light, but for an energy anomaly within the fountain itself. By carefully measuring the temperature and motion of the gas at different points in the stream, they could pinpoint a region that is inexplicably warmer than the surrounding material, a hotspot with no supernova remnant or young, hot stars to explain it. This warm core, hidden within the flowing river of gas, would be the ghostly signature of the dark star below. Its discovery would rewrite our understanding of galactic ecology, revealing that these fountains are not solely powered by stellar death, but are also sustained by the silent, ancient warmth of a star that never truly lived. A star that appeared a century ago and then vanished without explanation still haunts the archives of astronomy. This is the mystery of the ancient transient, a single point of light recorded on a glass photographic plate that defies all modern classification. Before the era of digital sky surveys, astronomers meticulously charted the heavens on these fragile plates, creating a permanent record of the night sky over decades. Buried within this vast library is a peculiar anomaly, a star that was not there in 1 year, shone faintly the next, and was gone forever by the third. It left no nebula, no expanding shockwave, and no progenitor star in its place. Modern analysis rules out a nova as the light curve was all wrong, too slow and too dim. It could not have been a supernova, for its brief glow was far too feeble. This single, inexplicable blip in the historical record is a perfect candidate for a dark star's brief awakening. The theory suggests this was not a star's death, but a moment of intense, visible consumption. Imagine a dormant dark star drifting through a local, dense knot of dark matter, a cosmic thicket in the void. As it passed through this concentrated cloud, its core would have been flooded with fresh fuel. The rate of dark matter annihilation would have skyrocketed, causing the star to flare with a sudden, soft brilliance for a short period, perhaps just a few years. This would have been a feast, a temporary surge of power that pushed its faint glow just over the threshold of detectability for the telescopes of that era. Once it moved through the dark matter clump and consumed the excess fuel, the annihilation rate would have dropped back to its normal, imperceptible level, and the star would have faded back into complete invisibility. To the astronomers of the past, it was simply a cataloging curiosity, a transient event filed away. To us, it is a ghost signal from a hidden population of objects, a single frame of a movie we are only now learning how to watch. The hunt is on to find more of these historical ghosts, to see if their brief appearances across the old plates form a pattern, a trail of breadcrumbs left by invisible giants as they graze on the dark currents of the galaxy. Some of the most puzzling galaxies in the universe are cosmic ghosts, vast in size yet almost empty of light. Astronomers call them ultra-diffuse galaxies. They can be as wide as the Milky Way but contain only 1% of its stars, leaving them so faint they blend into the blackness of space. The central mystery is simple yet profound. Why did these galaxies fail? With so much raw material, why did they not light up with billions of suns like our own? The answer might not lie in a lack of gas, but in a single, catastrophic success. A dark star could be the culprit. Imagine the early life of one of these proto-galaxies, a swirling cloud of primordial hydrogen and helium, seeded with dark matter. In this fertile environment, one seed grows faster and larger than all the others, drawing in vast amounts of gas and dark matter to become a true Leviathan. This first dark star, positioned at the very center of the infant galaxy, becomes a gravitational vacuum cleaner. Its immense pull does not just hold it together, it actively siphons the gas from the surrounding reservoir, the very gas that would have otherwise cooled, condensed, and formed generations of new, normal stars. This single entity acts as a cosmic bottleneck. By consuming the fuel for future starbirth at an incredible rate, it effectively starves the rest of the galaxy. The dark star becomes a glutton, a central engine that monopolizes the galaxy's potential, preventing the widespread ignition of stellar fires. The galaxy's evolution is stunted before it can truly begin, forever doomed to be a faint, sprawling shadow of what it might have been. This model elegantly solves the puzzle. We are not looking at a galaxy that was born poor, but at one that had its riches consumed by a hidden monarch. The dark star does not just hide in these galaxies, it defines their very nature, its ancient feast explaining their modern emptiness. Its presence would leave a subtle gravitational signature, a specific pattern in the motions of the few visible stars that could one day be detected. Finding this signature would mean we have not just found another dark star, but have unlocked the reason for an entire class of cosmic ghosts. That sudden, silent flash of gamma rays might be a dark star's final message. Across the cosmos, our telescopes occasionally record a brief, intense spike of the highest energy light, a burst that appears and vanishes in an instant. Unlike the colossal gamma ray bursts from dying stars, these events leave no fading afterglow, no expanding debris field. They are cosmic snapshots of a single, violent moment, and their origin remains one of space's most stubborn puzzles. One compelling theory points to a cataclysmic end for a certain type of dark star. Imagine the core of such an object, a dense concentration of dark matter particles that has been steadily annihilating for eons. If this core were to become unstable, perhaps from reaching a critical density, it could collapse in on itself. This would not be a gravitational collapse like a supernova, but a collapse of the dark matter field itself. The result would be a runaway chain reaction, a sudden, total annihilation of the entire dark matter heart in a single, catastrophic instant. The energy released would be staggering, channeled almost entirely into a brilliant, ultra-short flash of gamma radiation. There is another, even more exotic possibility. What if the dark matter particle itself underwent a fundamental change? A phase transition, akin to water instantly freezing into ice, could occur within the star's core. If the properties of the dark matter suddenly shifted, it could release an immense amount of binding energy all at once. This event would be a silent, invisible explosion from the perspective of normal matter, but it would flood the surrounding space with a powerful pulse of gamma rays, the only visible signature of the profound transformation happening within. The key to identifying these events lies in their unique fingerprint, their brevity, and their lack of an afterglow. Missions like the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope are perfectly suited for this hunt. Their instruments are designed to constantly monitor the sky for sudden flashes of gamma rays. By sifting through their vast archives of short bursts, astronomers can search for those specific events that have no counterpart in other wavelengths, no X-ray or optical echo to follow them. These orphaned flashes, these one-note symphonies in the gamma-ray band, could be the death certificates of dark stars. Each silent burst is a potential signal that something truly alien has just ended, a hidden giant that lived and died by rules we are only beginning to comprehend. Its final breath, a flash of light that crosses the universe to tell us we are not alone in the dark. A cosmic partnership forged in the heart of an ancient star cluster presents another profound candidate. Deep within a dense, spherical swarm of millions of stars, a silent dance is underway between two exotic relics. One partner is a pulsar, the rapidly spinning corpse of a massive star, beaming out a lighthouse pulse of radio waves with metronomic precision. Its companion, however, is utterly invisible to our telescopes, a dark star whose presence is felt only through its immense gravitational pull. This symbiotic pair, a dark star and a neutron star locked in a tight orbit, creates a natural laboratory of unparalleled precision. The pulsar is our clock. Every time it rotates, it sends a pulse of radio waves towards Earth. We can measure the arrival time of these pulses with astonishing accuracy, down to microseconds. If the pulsar is in a binary system, its orbit will cause a slight, rhythmic variation in these arrival times. As it moves toward us, the pulses arrive slightly more frequently, and as it moves away, they stretch out. By meticulously tracking this timing, astronomers can map the pulsar's entire orbit with incredible detail. They can calculate the mass of its invisible companion with perfect certainty. If that calculated mass is far too large to be a planet or a typical white dwarf, and yet the object emits no light, the evidence for a dark star becomes overwhelming. This setup allows for tests of fundamental physics that are impossible anywhere else. The way the two objects warp spacetime around each other could reveal subtle deviations from Einstein's predictions, showing how gravity behaves in the presence of an immense concentration of dark matter. Furthermore, the dark star's gravitational field would subtly tug on the surrounding cloud of dark matter within the cluster. This interaction would affect the density of dark matter flowing through the star itself, potentially varying the rate of annihilation in its core and causing minute-detectable changes in the orbital period over time. Observing this binary system would be like watching a perfect clock that occasionally and mysteriously speeds up or slows down for no apparent reason. Each tiny hiccup in the rhythm would be a message, a direct readout of the invisible dynamics between a dead star and a living phantom, a conversation written in gravity and time. The ultimate dark star candidate exists where physics breaks down. This final entity is a quantum black hole nexus, a theoretical object frozen in the moment of its own death. It is a star so dense it should have already collapsed into a singularity, but something holds it back, At its very heart, the known laws of gravity cease to apply, replaced by the strange rules of quantum mechanics. The immense pressure from its dark matter core is balanced by a quantum repulsion, a force born from the fabric of spacetime itself. This creates a stable, ultra-dense object, sometimes called a gravistar, a gravitational vacuum star. It is a dark star in its most extreme and final form. Its surface would not be made of atoms, but of an exotic state of matter, a boundary between our universe and whatever lies within. And from this bizarre surface, a faint glow would emanate. This is not the light of annihilation, but something even more profound, Hawking-like radiation. Just as a black hole is theorized to slowly evaporate by emitting particles, this quantum nexus would also leak energy due to its incredible density and the unique properties of its dark matter composition. It would be a cold, faint whisper of heat against the absolute cold of space. Detecting this signal would be the ultimate challenge, like trying to hear a single snowflake land in a silent forest. Its temperature would be barely above absolute zero, its radiation appearing in the deepest, lowest energy part of the electromagnetic spectrum. Finding it would mean we have not just found a new star, but a window into quantum gravity itself, a glimpse of the laws that govern the universe at the smallest scales, written in the faint, dying light of the largest dark star of all. The faint whisper of a quantum black hole nexus brings us to the final frontier of this search, the future technology that could turn these ghostly theories into confirmed reality. We stand on the verge of a new age of discovery, armed with instruments of unprecedented sensitivity. The James Webb Space Telescope is already peering back into the cosmic dawn, to the era when the first luminous objects ignited. It is not looking for dark stars directly, but for their profound influence. By analyzing the very first galaxies, Webb can search for anomalies in their light that point to an unusual power source. If it finds galaxies that are too bright, too early, or glowing with a strange chemical signature, it could be indirect evidence that their hearts were powered by dark matter annihilation, not just fusion. The sheer power of Webb allows it to see the fingerprints of these monsters in the ancient starlight they helped create. Meanwhile, back on Earth, the Vera Sea. Rubin Observatory is preparing for a different kind of hunt. With its colossal mirror and gigantic digital camera, it will photograph the entire visible sky every few nights for a decade. This monumental project will create a cosmic movie charting the subtle changes in the night sky. Within this river of data, the telltale signatures of dark stars could be hiding. It might catch the slow, rhythmic flicker of a binary dark star system, or the strange, wandering dot of a rogue star with an anomalous glow. The observatory's all-seeing eye is perfectly suited to find these statistical needles in the galactic haystack, objects whose behavior simply does not fit any known category. And then there is the music of spacetime, the planned laser interferometer space antenna, a fleet of 3 spacecraft flying in a perfect triangle millions of kilometers apart, will open a low-frequency gravitational wave window on the universe. This observatory will be tuned to hear the constant, low hum of the most massive objects in motion. It could detect the gravitational wave background from the early universe, a chorus that might be dominated by the vibrations of primordial dark stars. More directly, it could pick out the distinct, steady hum of a binary dark star system, a harmony of 2 invisible giants spinning in the void for eons. The discovery of just one confirmed dark star would send shockwaves through the foundations of physics. It would do more than just add a new entry to the cosmic bestiary. It would prove that dark matter is not just a smooth, invisible fluid, but can clump and collapse to form complex structures. It would reveal a new type of stellar evolution and a new way for the universe to create light and energy. Most importantly, it would give us a specific, tangible target to study, a laboratory where we could finally test the properties of the invisible particles that make up most of the cosmos. After a journey through 25 possibilities, from primordial giants to quantum phantoms, the hunt narrows to a single transformative goal: to find that first, undeniable signal in the data, the one that confirms we are not just living in a universe of stars, but sharing it with their ancient, invisible cousins. Finding a single dark star would be far more than just a new discovery. It would be a cataclysm for our understanding of the cosmos. Our entire model of stellar evolution, the beautiful and precise life cycle of stars from birth in a nebula to death as a white dwarf, neutron star, or black hole, is built on one fundamental engine: nuclear fusion. Dark stars shatter that foundation. They introduce an entirely new way for a star to be born, live, and die, one powered by the annihilation of invisible matter. Textbooks would need a new chapter, one that begins not with a cloud of gas, but with a knot of dark matter. This would force us to accept that the night sky, for all its brilliance, might be populated by two distinct populations of stars, the ones we see and their invisible cousins, living by a completely different set of physical laws. The implications ripple outwards, touching the very origin of life itself. If planets can form in the gentle, pervasive warmth of a dark star's habitable zone, then life could be exponentially more common in the universe, thriving in environments we once thought were utterly barren and frozen. We would have to expand our search for life beyond yellow suns to include these faint, twilight glows in the dark. The most concrete evidence would be for the nature of dark matter itself. For decades, we have inferred its existence only through its gravitational pull. Finding a dark star would be the first direct proof that dark matter is not just a smooth, featureless halo, but a particulate substance that can collapse, clump, and interact with itself. It would confirm that dark matter particles can annihilate, providing a crucial clue to their identity, and finally allowing physicists to move from inference to direct study. This discovery would also solve one of cosmology's greatest puzzles: the origin of supermassive black holes. How did these monsters, with masses of billions of suns, form so quickly after the Big Bang? A primordial dark star, or a quasi-star hybrid, provides the perfect cosmic shortcut. These behemoths could have collapsed directly into black hole seeds of thousands or even millions of solar masses, giving them a colossal head start. They are the missing link, the natural precursors that explain the rapid growth of the giants we now find at the center of nearly every galaxy. Ultimately, dark stars could be the foundational building blocks we have been missing. The first structures in the universe may not have been small, hot fusion stars, but these vast, cool, dark matter-powered giants. Their formation would have dictated the initial clearing of the cosmic fog, their radiation beginning the process of reionization, and their deaths would have planted the seeds for galaxies to form around. Our entire cosmic history, from the first light to the grand spiral of the Milky Way, might be built upon the silent, invisible framework of the first dark stars. Confirming them would not just add a new object to the celestial catalogue, it would rewrite the first chapter of our universe's story, revealing a dawn illuminated by a light we are only now learning to see. This search for cosmic ghosts requires a toolkit as diverse as the candidates themselves. Astronomers are not relying on a single method, but on a coordinated, multi-pronged assault, hunting for these invisible giants through the subtle traces they leave on the universe around them. One of the most powerful indirect methods is gravitational microlensing. Imagine a dark star drifting in the vast halo of our galaxy, perfectly aligned between Earth and a distant background star. As the dark star passes through our line of sight, its immense gravity acts as a natural lens, bending and focusing the light from that faraway star. For a brief period, the background star will appear to temporarily brighten, then fade, in a very specific, symmetric pattern. Massive surveys like the optical gravitational lensing experiment meticulously monitor hundreds of millions of stars, searching for these telltale flashes. A microlensing event caused by an invisible object with the mass of a dark star would have a distinct, long-duration signature, a clear signal of something massive and unseen drifting through the galactic dark. Alongside this, there is a direct search for the dark star's own faint light. While they do not shine from fusion, their dark matter annihilation engines are predicted to produce a unique photon signature. This would not be the broad spectrum of visible light, but specific emissions in the high-energy gamma ray and the low-energy infrared parts of the spectrum. The Fermi Gamma Ray Space Telescope constantly scans the sky, mapping these energetic photons, finding a persistent, point-like source of gamma rays with no visible counterpart could be the dark star's calling card. Simultaneously, the James Webb Space Telescope, with its incredible infrared sensitivity, could potentially detect the soft, warm glow of a nearby dark star's extended atmosphere, a faint heat signature against the cold of space. The hunt even extends to messengers beyond light. If dark matter particles are their own antimatter counterparts, their annihilation could produce a flux of neutrinos, those ghostly particles that barely interact with matter. Gigantic detectors buried deep in Antarctic ice, like the Ice Cube Neutrino Observatory, are listening for these faint whispers from space. A cluster of neutrinos seeming to emanate from a single, invisible point could point directly to an annihilation event within a dark star's core. And finally, there is the music of space-time. As we explored with binary systems, the orbital dance of two dark stars would generate a constant, low hum of gravitational waves. The Future Laser Interferometer Space Antenna mission is designed to be a colossal ear, tuned to hear this specific cosmic frequency. A confirmed detection would be the most direct proof imaginable, feeling the wobble in space-time itself caused by these invisible titans. No single observation will be enough. A true discovery will come from a convergence of evidence, a single object detected through multiple channels, a microlensing event that also shows a faint infrared glow, a source of gamma rays that coincides with a neutrino burst, or a gravitational wave signal from a location with no visible stars. This multi-messenger approach is the only way to be certain, to move from a compelling anomaly to a confirmed new class of celestial object, finally pulling these phantoms out of theory and into the light of our understanding. 25 cosmic mysteries now drift in our collective imagination, from primordial giants to quantum phantoms. Each one represents a frontier where our known physics meets the profound unknown, a testament to the creativity and persistence of the human mind trying to map the darkness. We have journeyed from the first flickers of creation to the silent, wandering ghosts in our own galactic backyard. This incredible variety reveals something fundamental. The universe is not merely stranger than we suppose, but stranger than we can suppose. Every dark star candidate is a question mark hanging in the void, challenging our most basic assumptions about what a star is, how life can thrive, and what truly powers the cosmos. They are not just hidden objects, they are hidden chapters in the story of everything. So the next time you find yourself under a clear night sky, look up at the familiar tapestry of stars. Remember that what you see is only the smallest fraction of what is actually there. For every point of light you can count, there could be a dozen invisible titans, dark and silent, shaping the universe from the shadows. The greatest discoveries are not behind us, they are waiting. They are out there now in the deep and wonderful dark, inviting us to keep looking, to keep wondering, and to never stop being amazed.